Hey everyone, and welcome back. Get ready because today we're taking you on a deep dive into the past, like way, way back to the early universe.
We're talking really early, like when the universe was just a fraction of its current age.
Yeah, seriously old, we're talking about an 8 billion-year-old signal. I mean, think about it. When this signal began its journey, Earth didn't even exist yet.
It's true, and it's really remarkable because this signal, which is what we call a fast radio burst, or FRB, gives us a glimpse into that early period.
It's like finding a baby picture of the cosmos.
You could say that.
Okay, I know we throw around FRB a lot on this show, but just as a refresher, can you remind us what those are again?
Sure, so imagine, if you will, the universe's most powerful firecrackers. That's an FRB. They're these incredibly bright, super fast bursts of radio waves. And when I say fast, I mean fast. We're talking milliseconds long. But get this. In that tiny sliver of time, FRBs release more energy than our sun does in days.
Days. It's mind-boggling.
Yeah, it really is incredible.
So this particular FRB we're talking about today has been given the catchy name FRB 2020-690. What makes this one so special? Why are we doing a whole deep dive on it?
It all boils down to distance. Astronomers have been detecting these FRBs for a while now, but this one is further away than any we've ever found before.
So it's like getting a postcard from the edge of the observable universe.
Exactly. This signal, it's been on a cosmic road trip for 8 billion years, traveling through space, interacting with everything it's encountered along the way. Just amazing.
So how did we even manage to find this signal? I'm assuming it took some seriously impressive technology.
You're definitely right about that. It took some of the most powerful telescopes we have. We're talking about the Australian Square Kilometre Array Pathfinder, ASKAP for short.
We talk about ASKAP a lot on the show, and for good reason.
Right. Well, this incredible radio telescope was the one that initially picked up on the signal.
Okay, but ASKAP is only one telescope. How do we know where the signal came from?
Good point. That's where another incredible piece of technology came in. To actually pinpoint exactly where this FRB came from, they used the Very Large Telescope.
Another powerhouse in the world of astronomy. Two telescopes working together to track down a signal from, what, almost halfway across the universe?
And it's not just how far away it is. It gets even more interesting. What they found was that this FRB originated from a galaxy that's not only incredibly far away, but incredibly old. We're not just looking at any random signal. We're seeing a signal from the very early universe.
A time when galaxies were just starting to form.
Exactly.
Wow, so what you're saying is this isn't just us observing a random flash of light here. We're potentially seeing the building blocks of galaxies billions of years in the past.
You got it. And that's what makes FRBs so valuable. They act like probes, carrying information about everything they've passed through on their long journey to us.
Which I'm guessing brings us to the missing matter problem that we hear so much about.
You got it. You know, it's interesting. The missing matter problem is a lot like a cosmic game of hide and seek. Well, our current understanding of physics tells us that there should be a lot more matter in the universe than what we're actually able to observe. It's a lot like, I don't know, baking a cake and realizing half the ingredients have just vanished.
That's one way to put it. So where did all this matter disappear to?
That's the million-dollar question, right? We do have some ideas, though.
Oh.
One of the leading theories right now is that this missing matter is hiding out in plain sight, just lurking in the vast, mostly empty spaces between galaxies. That's where FRBs, like the one we're talking about today, FRB 2020-2610, could be the key to cracking the case.
Wait, hold on. You're saying this signal, this one signal that's been traveling through space for billions of years, might help us find something we've lost in space.
It's wild, isn't it? But that's the exciting part about science. And it all comes down to how the FRB signal actually interacts with the matter it passes through.
Okay, I'm going to need you to break that down for me.
Think of it like this. If you shine a light through fog, the thicker the fog is, the dimmer the light becomes.
Right. Makes sense.
Well, it's kind of similar with FRBs. The more matter an FRB travels through, the more its signal changes, or it gets distorted.
Ah, I see where you're going with this. So by studying how this particular FRB signal has been changed over its long journey, we can get some clues about what exactly it encountered along the way. Sort of like a cosmic fingerprint.
Exactly.
Yeah.
You're getting it. And when we talk about analyzing those fingerprints, that's where the McCourt relation comes into play.
Okay, that term gets thrown around a lot. I'll admit it sounds a little intimidating.
I promise you it's not as complicated as it sounds. Basically, the McCourt relation is a way for us to predict how much an FRB signal should be distorted based on the amount of matter it passes through.
I see. So we can use it to measure the missing matter.
Exactly. And the truly exciting part of all this is that this recent discovery, With FRB 610A, it actually confirms that the McCourt relation holds true, even across these incredibly vast cosmological distances.
So we now know that it's a reliable tool for measuring matter, even in the furthest reaches of the universe.
Precisely. And the best part is, this is only the beginning. As we continue to discover more FRBs and study their signals, we can start to map out this missing matter in more detail.
And get a clearer picture of the universe's structure.
Exactly. Each burst we find is like adding a new data point, helping us connect the dots and reveal the hidden structure of the cosmos.
This is incredible stuff. And speaking of incredible, our sources mention that even more powerful telescopes are being built right now, ones that are going to be game changers for detecting FRBs. What can you tell us about them? These new telescopes sound amazing, but I have to ask, they're such huge projects. What's the driving force behind them? What's the ultimate goal?
Well, the truth is we're only just starting to understand FRBs. Right now, we're only catching a few here and there.
Right.
Imagine if we could detect thousands of them, or even millions every year.
Wow, that would be incredible. We could learn so much.
Exactly, and that's where these new telescopes come in. One of the most exciting ones on the horizon is the Square Kilometer Array.
The SKA.
That's the one. This is huge international collaboration, all to build the biggest, most powerful radio telescope in the world.
Yeah, we've talked about the SKA a few times on the show, and it really does sound like the holy grail when it comes to FRB research. What makes it so special?
Well, the SKA is going to be unbelievably sensitive. It'll be able to detect the faintest FRBs, even those coming from the furthest reaches of the universe.
Signals that we'd never even have dreamed of detecting before.
Exactly. We're talking about trying to detect signals so faint, it's like trying to hear someone whispering from across an ocean.
And with that much data, with all those FRBs, what could we learn? What are we hoping to find out?
It's not just about how many FRBs we can detect, but how accurately we can trace them back to their source. With the SKA, we'll be able to pinpoint exactly where in the universe these signals are coming from.
So we'll be able to create a kind of three-dimensional map of the universe using FRBs like signposts.
That's a great way to put it. Each FRB we detect will add another piece to that map, helping us figure out where the matter in the universe is and how it's structured.
And with that, we can start to unravel how the universe has evolved over time, from the Big Bang all the way to today.
Exactly.
It's amazing to think that it all started with this one 8-billion-year-old signal, and now we're talking about mapping the entire universe.
It really does make you appreciate how far we've come, doesn't it?
It does. It shows what we can accomplish when we push the boundaries of science and technology, all driven by curiosity.
I couldn't agree more.
It's enough to make anyone want to become an astronomer. So, as we wrap up this deep dive, what's the one big takeaway you want our listeners to remember?
I think the biggest thing to take away from all of this is that we live in a universe that is full of mystery, full of incredible things just waiting to be discovered.
And that with every new discovery we make, every new signal we detect, we get one step closer to understanding the grand cosmic puzzle.
Absolutely. And that's what makes it such an exciting time to be an astronomer, to be a scientist, to be alive. There's so much more out there just waiting to be found.
And that, listeners, is what the deep dive is all about. Thanks for joining us on this incredible journey into the past, to the very edge of the universe. We'll see you next time when we take another deep dive into another corner of the cosmos. Until then, keep looking up.